Hello everyone, I'm Xinyu Lian. I'm the first year PhD student from UIC. Today I'm going to present our papers, Universal Checkpointing, a flexible and efficient distributed checkpointing systems for large-scale DNA trainings with reconfigurable parallelisms. And that is joint work of UIC, Microsoft DeepSpeed, and the Snowflake AI research. So 3 years ago, we are training Bloom models with collaborations of hundreds of researchers. And the model was pre-trained with hundreds of GPUs with 3D parallelisms, including tensor parallelisms, pipeline parallelisms, and the data parallelisms with 0 stage 1. So unfortunately, after 3 months of trainings, we lost half of GPUs, but training haven't finished. So what can we do? Should we train from scratch? But restarting from scratch would be extremely costly. It means wasting 3 months of those expensive GPUs. So you may ask, is it possible to resume from the safe checkpointing using the remaining GPUs with new parallel configurations? But however, this introduces new challenges. So the challenge comes from the distributed checkpointing. So as you know, on the parallel strategies, the models are partitioned across GPUs. So each worker or GPUs independently save its own model states to the storage, including the parameters and normalized states, without synchronization overhead. So while this approach is efficient, it tightly couples the checkpoints to the original parallels and configurations. And here's some example to further illustrate it. So suppose we have 4 GPUs. So in pipeline parallelisms, each parameters may exist in only one checkpoint. In data parallelisms, the parameters are replicated across all the checkpoints. And in tensor parallelisms, the parameters are split horizontally or vertically. And for more specific models like MOE, mixture of expert models, and GQA, which is grouped query attentions, the tensor parallelism can involve non-conceptual sharding patterns. And additionally, in a synchronization training setup, the same parameters may have different weights across workers. Therefore, distributed checkpointing have very diverse patterns that couple to the model parallelisms. And fault tolerance is also a critical challenge in large-scale model trainings, as reported by the Llama papers. So during training of Llama 3 using more than 10,000 GPUs, there are more than 400 failures, roughly 1 failure every 3 hours. And there are 2 potential solutions. One is to maintain a reserved pool of spare GPUs for live replacements, or to enable training to adapt to the fewer GPUs. But this requires to assume trainings with modified parallelism strategies. So similarly, when translating from pre-training to post-training stage, which typically require fewer GPUs. And real-time evaluation of downstream tasks also demand fewer resources. And also when you use slalom-based resource allocations, it's very difficult to guarantee the same number of GPUs during allocations. And also, which means if a previous job allocation is expired, we may either fail to match the original GPU numbers or face a very long clean time. So therefore, one challenge for checkpoint systems these days is to support flexible change in parallelism strategies. So in this work, we developed the universal checkpointing. It's a novel checkpoint systems that enables reconfigurations across widely used parallel strategies, including tensor parallelisms, pipeline parallelisms, data parallelism with any 0 stages, and the sequence parallelisms, and more. And also it's compatible with both dense and MOE models. And we also introduced several efficiency optimizations to reducing the reconfiguration overhead to less than 0.001% of training times. And the universal checkpointing has been open sourced in DeepSpeed and be adopted by organizations such as Microsoft, Big Science, Baidu, UC Berkeley, and others for large-scale model training, including pre-trainings and fine-tunings, including 5.3 MOE from Microsoft and Bloom models and then multi-models. And this has been tested on large-scale clusters with thousands of GPUs, including AMD and Intel GPUs by the Oak Ridge National Lab and Argonne National Lab. And it has been selected for presentation at PyTorch and FMS this year. So as discussed in the previous slide, there are a few methods to deal with it. So if a GPU fails, one option is to wait for the fault GPUs to be physically replaced. But this approach requires maintaining a reserved pool of spare GPUs, which remain idle during trainings, resulting in inefficient resource usage. And if the slump job allocation is expired, we can wait until the same number of GPUs become available to resume trainings. But this may result in hours or even days of waitings. And a more common manual workaround is to write an ad hoc conversion script to adapt the existing checkpoint to a new parallel configurations. Well, this is possible, but the method is kind of error-prone, time-consuming, and not scalable to large-scale model or production environment. And here's a simple examples. So suppose we start from 8 GPUs. In each block, we show the parameter sharding layout of different parallelism configurations. And then we want to resume trainings on just 4 GPUs with a different parallelism configurations. And also, we want to try different target parallel strategies to compare throughput and select the best one, most efficient ones. So this means you need to write n conversion script for n target configurations. So in total, for n source and n target configurations, we will need m times n ad hoc scripts. And as the number of GPUs and the configuration options increase, the number of required conversion grow rapidly, making this approach highly inefficient and impractical for large-scale training. So therefore, we propose using our intermediate checkpoint representations. Instead of writing an ad hoc script for every possible pair of source and target parallelism configurations, we first convert the source format into a unified intermediate representations. And from there, we can convert to any target configurations. So here we introduce atomic checkpoint, a fine-graded parameter level format designed for flexible and efficiency. So this fine-graded level representation enable efficient parallel conversions and reduce contention during the processing. And the atomic checkpoint store both model parameters and optimizer states, allowing training to resume with full optimizer context, including momentum and variance for the atoms. So importantly, this atomic checkpoints format is decoupled from any specific parallel strategies, making it adaptable across different configurations. And it also includes some metadata such as training iterations and the learning rate scheduler and other essential runtime informations to support full recovery. So based on the atomic checkpoint, can we simplify the process of converting distributed checkpointing from the source parallelism configuration into the optimized atomic checkpoint format and then remap back? So most importantly, how can we ensure that this conversion process is generated to both widely used strategies and various model architectures? And also to make things easier and automatically, we build a pattern-based reconfiguration pipeline. First, we predefine the reconfiguration patterns, and this pattern can guide how tensors are going to be transferred. So unique tensor is commonly in inter-parallelism, such as pipeline parallelisms, including interleaved pipeline parallelisms, and the optimizer states for the 0 stage 1 and 2. And the replica is commonly in the data parallelisms, and also some bias and the normalization terms in the tensor parallelisms. And partial pattern is normally used in the asynchronization trainings. And the sharding V and the sharding H, which means vertical and horizontally, is commonly in the TP, and also some 0 stage 3 is DP. And the sharding hybrid and the sharding non-constructive is kind of can be found in specific models like MOE or GQAs. And for each pattern, we have corresponding operators for it. So for example, we can reduce redundancy for the replicate patterns, average the tensors for partial patterns, and concatenate the sharded tensors on arbitrary dimensions to enable automatic scalable mappings between different checkpoint structures. So next, I will introduce efficiency optimizations. So 3 years ago, when using universal trap pointing without any optimizations, so reconfiguration a model such as Bloom models can take up to 45 minutes. So which is impractical, and when we need to change the parallelism strategies frequently, and when we need to, the model needs to scale up. So in this work, we propose several optimization techniques to address this, including nested parallel reconfigurations, and the redundancy bypassing loadings, and the lazy reconfiguration invocations. So due to time limits, I will focus on the first one. So for details of the later two, please refer to our paper. So we found that one of the main bottlenecks comes from the PCIe bandwidth between a single CPU and the storage if we do the conversion in sequence. And given that we only have multiple nodes, each with multiple CPUs, can we leverage those resources? To address this, we introduced nested parallel with 2 layers. The first one is outer parallel. So we formulated the reconfiguration as a MapReduce problems. So this allows us to distribute and parallel conversions using the aggregated PCIe bandwidth. And the second one is inter parallel. So within each node, we can take advantage of multiple core CPU processings. So all the available cores are engaged to perform fine-graded reconfigurations task concurrently. So those ensure that we can fully utilize the computation powers within a single machine. So to evaluate our systems, we run experiments on pipe datasets with diverse model architectures, including dense and MOE models of different model sites. And we test across both NVIDIA and AMD GPUs, scaling up to thousands of devices. So in the experiment, we first verify the accuracy of the universal trap pointing, which means whether UCP can enable reconfigurations parallelisms without training loss. So what we did is we run the source parallelism configure for 200 iterations and record the training loss. And then we resume the training with the saved trap point at iteration 100 and check whether the training loss between the iteration 100 and 200 are overlapped with original one. And we did extensive experiments with broad combination of parallelism configures, with combination of the tensor parallelism, pipeline parallelism, sequence parallelism, and the data parallelisms, and for any 0 stages. On left, we resume from a single source configurations and resume training across multiple target configurations. On the right, we did the opposite. We resumed into one target configurations from the checkpoint saved by the multiple source configures. So you can see from a figure that on both sides, the training loss with all the configuration strategies is overlapped, and the loss curve remains smooth and stable. And we also evaluate UCP on diverse model architectures, including MOE models. And note that the training loss curve in the middle is a real-world case during the Bloom pre-training. And we also evaluated overhead introduced by reconfigurations. So it's important to know that UCP does not modify the checkpoint saving logic, meaning there's no additional saving cost. And the UCP is also compatible with advanced checkpoint technique, such as asynchronous savings. So compared to a sequential conversion method, so UCP's nested parallel approach achieves up to over 200 times reductions in conversion times. And as shown in the figure, even for 1 TB models, the reconfiguration time is under 3 minutes, which is negligible to the total training times. So in conclusion, we introduced universal trap pointings, a novel trap point system that enable flexible and efficient reconfigurations for both sets of the widely used parallelism strategies and their combinations. So our work has been adopted and tested by the Microsoft, AMD, and Big Science Baidu, and the 2 national labs for large-scale model pre-trainings and fine-tunings. And here's source code and some tutorials from DeepSpeed and Megatron DeepSpeed and Hugging Face. Welcome any questions. Yeah.